Hello everybody, welcome to unit number 9. This unit is very difficult because it involves probability and some of you really don't understand how the probability works. So it's difficult, but let's try to make it as easy as I can. I'll try to make it easy for you. So this week I am not doing the audio listening for each of the slides because it's complex, and for me I have to go into show you more visually what really is happening. So try to watch this video, try to follow me, and then sure, it will be easy. So let's go to some of the basics. I'm gonna disappear from the image because I need to use full slides in order for us to explain everything. Okay, so let's go first to understanding probability. So in this one we're gonna go to understanding probability. So what is the purpose of understanding probability? I'm gonna bring this in. Okay, so in this case we have sometimes we have uncertain situations. In these uncertain situations, the thing is, like, we're gonna try to guess what will likely happen. Okay, so when we're talking about this in business, that means that, for example, we have the production or manufacturing of a certain product. So what is the likelihood that the quality is not going to be accurate or the quality is going to be defective? So in this case, we have to roughly have a number of what is the likelihood that can happen. So it can be, maybe if we know it's going to fail only 1%, so we have to do a lot of trials and errors. So that's pretty much a probability. How we get the probability? By trying, let's say, 1,000 out of 1,000 times from the previous production process. Now we know that it's gonna fail only 1 or 2% based on that. So if there's any variables changing, how that percentage may change. Let's say, if we, for example, if we fired employees, if there's gonna be any changes on that. So we have to understand that very well. Okay, so in this case we will be using numbers to recognize what is more likely to happen. Okay, so let's look at this a little bit here. Okay, here, for example, let's look at an example. So in this case, for example, we have your division is just about to decide whether or not to introduce a new digital audio tape player into the consumer market. Although your marketing studies show that typical consumers like the product and feel that its price is reasonable, its success hardly assured. Uncertainty comes in many factors. So in this case, for example, this is a case where we have what would the competition do? Will your suppliers provide quality components in a timely manner? Is there a flaw that has been not noticed yet? Will there be a recession, expansion economy? So we have a lot of variables that can happen. So in this case, we're gonna do a study, and then we're gonna try. Let's say, for example, what we do is, based on the previous example, we have a component, we produce it 10 times, and based on those 10 times how many failed is what we call the sample space. Okay, so let's say, for example, in this case, in the previous example that I mentioned in the previous slide, we have 10 times, 1, 2, 3, let's just do it 5, because if not it's gonna take me forever. So we try 5 times. So in the first time it was not defective, second time it was not defective, first time was defective, third time, fourth time it was defective, and fifth time was not defective. So that is the possibilities, a list of the possibilities, a piece of list of possibilities. Every time we have, that is, we have 2 sample spaces. Well, we have 1 sample space, but we have 2 possibilities. That is defective or not defective. Okay, so those 2 options is what we call the sample space. If we were to look into a coin, it's heads or tails. Okay, there's only 2 options in the sample space. Okay, so in this case we have, there's 2 probabilities. In this case, like I said, because we run this experiment 5 times, we know that the 2 out of 5 is effective. So in this case, we have already that sample space. Okay, very good. So now, okay, so that's what I mentioned just now is called what is called the random experiment. So in this case, for example, in a controlled way, like I told you, in a controlled way, I measured, for example, in that measure, the production of that manufactured item. No, so in this case, I have 1, 2, 3, 4, well, 5 already, 6, 7, 8, 9, 10. Okay, so I tried 10 times. The conditions are gonna be exactly the same. Okay, that's why it's a random experiment, but somehow it's controlled, because in this case we have we have to eliminate any vagueness or surprise. So we have to carry exactly the experiment. The random experiment must be random, as in we don't know what's gonna happen, because that's probability. But at the same time, we know that there's gonna be an outcome. So in this case, like I said, we have 10 times we tried it on the same conditions. For example, in this case, what means the same conditions to be a random experiment that is valid? It's valid because these 10 times that I produced that specific product, they were the same employees, okay? It was produced at the same time, and it was produced with the same level of material, okay? So if I change one of, like, let's say for example, the material, I add less material on this one, on this trial, then that's not a valid random experiment. Then that's already manipulated, and that will affect the probability. Okay, so that we have to make sure that the random experiment is controlled, is under a control situation. Otherwise, if we try it in different ways in different times, that affect the probability, and that is not what works with probability and statistics. So in this case, like I was saying, in this case we have the sample space. So is the possible outcomes, like I explained before when I talked about the defective part, the sample space was only one defective or not defective. Okay, two possible outcomes. Now in this case, for example, let's look at a larger sample space. So in this case, for example, a focus group for marketing is choosing the design of a new reading lamp. So they have designed different lamps: one lamp, 2, 3, 4, 5, 6, and 7. So there's 7 probabilities in the sample space. So this is the sample space, 7 types of results. In the previous one, the sample space was only 2 because it's defective or not defective. So in this case, I can say that the probability is 1 out of 2, but in this one is the probability 1 out of 7 if I give to the consumers to choose whatever they like. Okay, so now, so based on that sample space, we have the probability outcomes. So in the probability outcomes, that means that something actually happened. So after, let's say, the random experiment in here, like I was mentioning, is a controlled, okay, random experiment, it's controlled, right? Random experiment is controlled because we're gonna show them the lamps in exactly the same conditions. So I'm gonna go to as a consumer and say, okay, consumer, I have 7 different lamps in here. Look at this lamp. Lamp number A, design B, design C, design D, etc. Okay. So for it to be random and valid, I have to show them exactly in the same way. What happens if, for example, I show them the design B under a condition where is the weather, or well, the conditions, the aircon is very hot. So they're just thinking like, oh, I'm so tired, I don't want to see any lamps anymore. No, everything must be in the same way. Or what happens if lamp C is very dirty because they just brought it the prototype from the factory, so that already affects the outcome. So we have to make sure that in the sample space everything looks exactly the same in order to be valid, the experiment to be valid, and then we will have an outcome. So what is the outcome? Is the result. So in this case, the most chosen lamp was a design D. Okay, so that is the outcome. So there was a probability of 1 in 7 that the outcome will be D, right? Or maybe they already have some pre-established probability because they say, we think that based on the previous results, we think that A is going to be chosen. But in this case, D is actually the one that was the outcome, the result. Okay, think of the result, the result as the outcome. So now, so in this case, we have the event. Okay, so events, in this case, we have an event is something you care that might happen. So the formal definition of an event is any collection of outcomes specified in advance. So in this case, you can have this random experiment. So in this random experiment, let's say for example, random experiment, we have, for example, one event design for the focus group. Consider the event. The chosen design is easy to produce. This is an event. Okay, so in this case, since the observed outcome design D is not in this list, this event did not happen. So here, for example, there was A, B, C, and F. So this event did not happen. Okay, don't get too complex in this one. In events it is just a result of the experiment. So it is just, for example, when we go back a little bit into this one, we were saying, for example, in understanding probability in the sample space, or where's the sample space? I'm gonna remove this. In the sample space, we have multiple outcomes of one event. Okay, so what is the event? Choose the most likely to the lamp that you like the most in this sample space. So in this case, it just happens that maybe design E, so that is the outcome of that event, or that somehow that experiment. This is too technical, but you're going to understand it better with Excel. So anyways, so in this case we have the events and the probability of events. So how likely is an event? So in this case we have the probability of interpretation. So in this case, what is the likelihood that a certain lamp is chosen? So in this case we have the probability interpretations, and we have that we have what is the likelihood that it happens. So the likelihood that the lamp is chosen is, for example, the lamp is gonna be always chosen. That's a probability of 1%. But in this case, the probability is decreasing because there's more lamps. Okay, so let's say, for example, if we were to have only 2 lamps, okay, 2 lamps, that means 50% and 50% that this event or this outcome may happen. But the more lamps we have, the less likely it's gonna happen. Then it's gonna decrease. The sample, if the sample space is larger, the likelihood that this happen, it starts to decrease, right? In this case, for example, if we have six different lamps, then the probability starts to get much lower. So the probability is 1 out of 6. So it's better to have the probability 1 out of 2 than the probability 1 out of 6. Okay, so that's how we interpret this probability. And again, it goes together to what is going to be the result. What is the likelihood that this event may happen or not? What is the likelihood that a certain lamp will be chosen or not? Okay, so how do we determine these probabilities? How do we say, is it only from the sample space? No, it may come from different ways. When I was saying it relies, for example, just now I was talking about in the sample space, based on the sample space, based that there's two outcomes, I was using somehow the theoretical probability by formula, so that that one is going to happen 1 out of 2 times. Okay, let's look at that. Let's look at that. That is a theoretical probability. So in this case, I can say the coin is tossed. It may happen 1 out of 2 times. So in this one, the event may have number of favorable outcomes, total number of possible outcomes. So it's 1 divided by 2. So that one is just the 50. Okay. So in this case, that is the theoretical probability. I already used it. It can be the relative frequency, and this one is exactly relative frequency. It's happens in the other way around. Means, how do I come with this probability that this may happen is based on the number of times that I do it. So the more times I perform it, the most likely that is more accurate. Okay, so let's say, for example, if I throw a coin and I throw it only 2 times, and the 2 times is head, so is that experiment or that event valid? It's not really valid, because the outcome is already somehow, it's only 2 times. I cannot really address well that is most likely to happen in the future. So then I will have to throw the coin 100 times to get a more accurate number. So that is what we call it more in the relative frequency. So in this case, in the relative frequency, means because we have tried many times, it is more likely that in the future, if we carry that experiment, that may happen in that way. Okay, so, and this is what we call here, that is a relative frequency. So like I said, if I try many times, there is more likelihood that something behaves in the same way in the future. Why? Because our assumption is based on a lot of trials. If we try a lot of times, then of course we get a much better a result. Okay, so in this case, let me pass to this one, which is called the law of the large numbers. The law of the large numbers pretty much goes together with that, which says if we want to have a more accurate prediction, let's try it as many times as possible. Okay, and that goes together, for example, with marketing. Let's look at the application of the law of the large numbers in marketing. So let's go to this lamp. What happens if, for example, I give to choose to only 2 consumers about these 7 lamps? So in this case, the outcome is not gonna be effective because I have only 2 people choosing. So maybe one, like, I'm biased because only one choose the design A and the other one choose the design B. So then I can say like, oh, we made an analysis, and based on the consumer preferences, they like lamps A and B. Does that represent the reality? No, that doesn't represent the reality. We will have to call in 100 consumers and then make them choose. So, and that is when the law of the large numbers may go into effect, when we say the more we try, the most likelihood it reflects the reality. Because of course the number of people choosing is much larger. The number of events is larger. Okay, sample space remains the same. So in this case, the sample space was 7, but the events were 100 times. We tried 100 times. Okay, so in this case, we have 2 types already, 2 types of observation. Relative frequency, like I said, the more we try, the more accurate would be. Theoretical probability, which is by a formula, we do it based on a calculation that is like just dividing the sample space. The likelihood is be 50-50, no, or 1 out of 7 in case of the lamps. And then we have the subjective probability, which is by opinion, which is maybe an expert already. There's an expert involved and says like, well, in the case of the 7 lamps, the most likely to be chosen will be a lamp, the red lamp. Why? Because consumers, I have realized throughout my history that every time that I create blue lamps, they don't like it. But when they have the red one, the likelihood that is that maybe 7 out of 10 will like it. So this is subjective probability because we cannot really back it up with numbers. It's just based on experience by someone. So in this case, we don't use the any theoretical or relative. It's just based on what they have seen before. Okay, so this is somehow subjective probability is the least accurate out of all of them, but we use it a lot. Also, we use it a lot because sometimes, although it's less accurate in terms of number, also its subjectivity also helps to address it in a more qualitative way. Sometimes quantitatively we can say numbers prove this, but qualitatively there's a different story because the consumers have chosen something very different before. Okay, so that leads us to dependency of events. So in this case we have two types. We have two types of events. Okay, so in this case, for example, when I was talking about the events, the lamps, choosing the event of choosing a lamp. In the event of choosing a lamp, we have is mutually exclusive because I can choose only one type of lamp or not. I can choose two types of lamps. That depends. Okay, so in this case, for example, choosing the lamps is not mutually exclusive because I could choose two at the same time. But in this, for example, in the case of heads or tails, I can only one can happen. So in this case, they are not mutually exclusive because two things can happen if the consumer chooses a different one. Or I can make it mutually exclusive if I say, if you choose this one, you cannot choose this one. Okay, so anyway, mutually exclusive, like I said, is things that cannot happen at the same time, heads or tails. So that's it. Okay, they cannot happen at the same time. They cannot happen that you throw and you have heads and tails at the same time. And then we have acts that are independent, in this case regardless of the previous throw. So in this case, this one, for example, the events of choosing the lamp are independent because consumer 1 does not have any connection to consumer 2 or consumer 3. Okay, they are independent. So in this case, they choose independently and they don't affect the result of the other one. Okay, so in this case we have to look at, regardless what happened in the previous choice, this consumer is not affected by them. And the same thing, for example, regardless of the previous throw. And this one, I'm gonna give you one example that says, like, for example, in a soccer match there's a team red and team blue. So whenever team red and team blue meet on all the previous games, team red has won. Okay, or out of 10 times that they met, 9 times team red won. So the probability is at 90. But in this event, every single game is independent. Not because on the previous game team blue lost, that doesn't mean they cannot win on this one. So still independent. Regardless what happened on the previous game, this game is different. Okay, and that's why they are independent events. Okay, and then on mutually exclusive, you can either just, well, actually you can tie. You can win or lose. Okay, that's it. You have only mutually exclusive. Yeah, in this case, for example, if I add to the game tie, then the mutual exclusivity, then it's gone. Okay, good. So now let's go through best way to solve probability problems. So in this case, what we're going to be using this time is probability trees. This one we use them mostly for business. What is the best or the most likelihood that we're going to choose a certain outcome. Okay, so in this case, for example, let's look at the first case. So in this case, for example, we have a case where, say, system support is demanding tasks. Some customers call to ask for advice on how to use the system. Other needs help with problems they are having with it. Based on the past experience as managers system support, you have to use some probabilities for a typical support call and summarize in your results in the probability tree shown. So it says It says starting from the left, note that the probability of the event irate color is 20% and 80% were not irate. So when someone calls the call center, based on your previous experience, 20% of them are already upset and 80% are not upset. And then we have some other areas. Okay, so in this case we have here already sample space. So in the sample space, that means yes, they can call angry, no, they are not angry. Okay, so sample space is 2. So the outcome, there's only 2 outcomes in this sample space. Sample space is only 2. You have 2 outcomes. So in this case, what is the event? The event is a call. Okay. These ones are mutually exclusive because it's either yes, you're upset, or no, you're not upset. Okay, so they are mutually exclusive. And there's one also, the call is also an independent event. Why? Because independently of what the previous consumer, if the previous consumer was upset or not, the next one may be or not upset. So we already start to set up a little bit of what this probability is going to tell us in terms of the sample space, the event, and the outcomes. So we need to understand that first before starting to do absolutely anything. Okay, very good. So now, based on previous experience, we have that 80% are not upset and 20% are not upset. Okay, but we have more to it. If you read the case created in advance, also it says whether once the guy called, they're upset, and then were we able to help them? Yes and no. Then it divides one more time. It says out of these 20% of people, 50% were helped and 85% were not helped. Why? Maybe because they were upset. And from the other 80%, 70% of them were able to be helped, and then 30% of them were not able to be helped. So now in this case, we start to play with the probability. So let's go one more time. There's a probability that they are upset or they are not upset. If they are upset, they also have the probability that I help them or not. Okay, so in this case, like I said, this one, for example, here we have to divide this sample space already into 2. Like I said, the event happens or not, so that's why this one is 100%. It must happen 100%. Either you're upset or not. So if I add 0.20 plus 20, it's going to give me 1. Why? Because this event must happen. Okay, and the same thing continues on. Can it be helped or not? Then is also this one sums 1. Why? Because it 100% must happen. Either I help you or not. That's the outcome of the event. And the same in here. Either I help you or not. Okay, so now in this case, what we have in here is we have the multiplication of the the chance that this may happen. So in this case, for example, we have here 3 and plus 17 makes this 20%. Okay, and then we have 56 and 24, then makes the 80%. Okay, so give me a second. So in this case, what we have to do is to multiply this probability, this probability times the percentage, so that it can give us this number. Then this one times the probability, so it can give us this number. and these two together are this 20%. Okay, very good. And now, like I said, this is a sample space of 100%. So if we add all together, if we add everything together, this also must make 1 or 100%. Okay, because in this case, so what I want to know ultimately was whether the consumer was helped or not. So in this case, I can see that the probability that the consumer was helped is, end of the story, it was 56. So that I can say as a manager of this center, I can say 50% of my calls are either they I mean, in this case, they were not upset, but I solved it. So when consumers are not upset, it is more likely that I can help them. This is the biggest likelihood so far. Okay, so in this case, for me as a manager, as a business manager, I need to figure out how can I improve these numbers. Okay, so that perhaps I can do help them. Yes, it's very, very low. When they are upset, mostly I cannot help them. So I have to figure that out. So you realize here that only help them 3% of them. 3% of them is helped when they are upset. So we have to take care of our consumers. And also the same thing. You see this, we're not upset, and also it's at 24% is very large. So we have to be careful of that. Okay, so now, so in this case, that is how we solve the probability trees. And in the end, the final outcome is, like I said, the most important thing, which is, in this case, what I have to find out is which one has the largest one. So the largest one is this one and this one. So that means out of the 100% of people, all this percentage, we are helping them. Okay, so in this case, this 20%, okay, within this 20%, 17 we don't help them, and out of this what is this 80%, out of this 80%, 24 we're not helping them. Okay, not helping, not helping. So if I put it together, then this 24 and this 17, that means that I still have a large number of people not being helped, and I don't think that's very good for the company. So in the end, that is how we have to guess the likelihood of what can happen. So in this case, for example, this is based on the previous experience, or it could be on the previous month. So for the next month, what we have to do is, if the consumer calls very upset, 20% of them are going to call you very, very upset. So for me, I can say, as a manager of human resources, you're going to receive calls, but okay, don't worry, because only 20% of them are very upset. So try to improve that, try to calm down, try to address them in a different way so that you can help them, so that we can increase those numbers. Okay, so that maybe we want the full 20% to be attended, and that already raises our statistics, because in this case I can say the same thing. Not because they are happy doesn't mean that you're not gonna help them. So the same thing, when they are called happy but they are complain, also try to address them, try to help them, so that we can raise these numbers to 100%. 100, that's the ideal, that 100% of the time we help the consumer, regardless they are upset or not. Okay, so that's how it works in there. So now let me pause, let me go to another example. Well, let me rephrase this. In this case, this is what I was explaining to you just now. Wait. What I was explaining to you just now is exactly this, which is this one must add to 1, because in the end it happens 100%. Okay, then regardless how many divisions we have, also this must add to 1, because it also happens 100% of the time. This one also must add to 1, must add to 1. Okay, this and this is the sum of this. So if it was 20%, regardless how it changes, say for example, maybe 3 and 17 permutations are endless. Yeah, I can say 5 and 15, I can say 10 and 10, but regardless it's 20, and then the other one must be 80. So the same thing here, these results must be, those permutations must be the same thing, 60 20, 50 30, etc, etc. Okay, and again, these results, this times this and equals this one. So again, this times this equals this one, and the same for the bottom. We'll just one day up and then one at the bottom. Okay, very good. So now in this one, so now this one is a very simple example. It's the same way. I want you to do it on your own. So in this case, we have the same thing. This is for drug testing. So the probability, this one is about employees. What is the probability of finding employees that are a drug user? So in this case, you have estimation that how many of your employees consume drugs, and you want to find out. And so we have the same thing. Also, we have a case where we want to try that, and we'll say, okay, so you drug use, yes or no. Okay, 100%. So in this one, test positive, no. Let me change this. So in this case, we have 92% no, only 8% yes, but within that one still can, I mean, you use drugs, 92% no, and then even if you consume drugs, there is a likelihood that you test positive and no. Why? Maybe it's not in your blood, I don't know, maybe the drug that you're using has no traces of the drug. So in this case, that's why we do that probability tree one more time, and then we get the result. Okay, so this one, try it on your own. Actually, I will encourage you more, rather than doing these examples. These are a bit more complex to what we're doing in Excel. In Excel is much easier, and you will understand it much easier. So don't worry too much if you are not understanding this right now. Okay, understand. If you don't understand in Excel, then you start to shake your legs, because then that's difficult. So okay, so make sure you try to understand this. This is part of your final exam. In your final exam, you will have to do a probability tree, and then you'll have to find the result, and you will have to find the expected monetary value. Here in this one, I was just doing the probability without expected monetary value, but in the exam, we're going to do it the same as in the Excel that you will do for your assignment.